Anyway, when last we met, we configured the peripherals necessary to blink an LED once per second. We put them in the program here. So all that was needed left was the interrupt handlers. Now, what is an interrupt handler? An interrupt handler is a routine that runs when an interrupt, external or internal interrupt, occurs to handle whatever interrupt is being declared or being generated. As you can see from all these interrupts here, there's a lot of options for the interrupts for this processor and any processor in general. The only one that we're going to be dealing with is the RTC counter in overflow or compare match interrupt. This interrupt right here. So when it gets triggered, it goes to this line of code and it will jump to this label. So we go back down here after our main loop and put that label for where we will have the interrupt handling routine. Now, let me pull up the there. The interrupt handler for this is going to be for the real-time counter. And when we look at the registers for the real-time counter, we see that there's a interrupt flags register that will indicate which interrupt brought us to the interrupt handling routine. They are not in separate handling routines. So the flag will tell us whether it's a compare or an overflow interrupt. But in actuality, it doesn't really matter, because what we're going to do is whenever the interrupt is triggered, which would be every half second, we'll just toggle the pin on port C, pin 6, off and on every half second. So the interrupt handling routine, let's look at the interrupt flags. This flag is set when the value from the count register matches the value in the compare register. Writing a 1 to this bit clears the flag. That's important. This little statement here is important. Writing a 1 to this bit clears the flag. Not writing a 0, which you would intuitively think that you would write a 0 to clear a flag. Instead, it's writing a 1. So, in the interrupt handling routine, first of all, we're going to turn off global interrupts so that no other interrupts get called while we're in the interrupt handling routine. That is the clear the I bit command, CLI. Then we're going to clear the flag that brought us here. Now, it's going to be a 1 in either the bit 0. Go back over here. It's either going to be a 1 in bit 0 or a 1 in bit 1. How do we know which one it is? We read that register and find out which one it is. Okay? So we're going to load that register into register 16. So LDS R16 0x0143, because it's the base address is 140 and the offset is 3. If I'm remembering correctly, yes, the offset is 3. So you add 3 to the 140, get 143. You read it to the register 16. Then, to clear the flag, you need to write a 1 where there's a 1. How do you do that? Just write the register value back to itself. Because there's going to be 1 there for the flag that brought us here in one of those 2 locations, bit 0 or bit 1. So you store it right back. All right, and that will clear the flag. Now now we have to toggle the pin 6 of port C. Well, how do you toggle something selectively? What logic function is that? Where you selectively invert it. Yeah, it's one of the gates. Let's see here. Because the is 0, 0, 0, 1, 0, 1, 1. Right? For the exclusive OR. Remember that from the digital logic? Kind of, sort of? Okay. So if it's a 1, if you're exclusive ORing with a 1, the output's going to be the inverse of B. If the A is a 0, it's just going to remain B. So this will selectively invert the value on a pin, right? If A is a 1, if you're selecting invert it, it takes the inverse of B in both lines. Okay? So get rid of that. Okay, so we need to load that port, that value into R16. and that's the out bit, the out register of port C. Now, if you took notes and wrote down the port numbers that I gave in the last time we met, we load into R16 0x0444. Now there is a, let's see here, looking at the instruction set, come on, you pass this nonsense. Oh, where's the instruction set summary? Come on. Oh, okay. So I need to go to instruction set manual and instruction description. There is a command. Exclusive OR. And it takes the exclusive OR of 2 registers. So you would need to load immediate R17 0B01000000. You want to exclusive OR bit 6 with a 1 to invert it, right? So you have to load the 1 in the 6th bit of R17. Then you can EOR R16, R17. And that will invert the 6th bit of R16. Then you store that back to the out register of port C. That's all there is to it. Load it, invert the bit, put it back. So that being done, because we turned off the global interrupts, we want to re-enable them. So we'll SEI set the I bit in the global interrupts, and then we will return from the interrupt handling routine, which is RETI. So that's all there is to that handling routine. And I want to say that's it for the program. Yeah, you jump to from when your first power's on, jumps to start, configures the clock, configures the interrupts, configure port C pin 6 as an output, configure the RTC, enable the interrupts, enable the timer, and then do nothing until an interrupt occurs. And then The interrupt handling routine clears the interrupts, global interrupt flag, clears the flag that brought us here, and then toggle the bit bit 6 of port C, turn on global interrupts, and then return from the interrupt handling routine. Now let's see if it works. Yeah.
I mean, I was just gonna ask you, so like right there in port C, you are at 0, 4, 4, 4. But if you go back up into, I think it was right here, or 6, port C to port 6 as an output.
Yeah.
We set it to 0x440.
Yes.
Is that why did we do?
Well, let's go back to the register description of the ports.
Offset? Is that what it was?
Yes, a register summary. Register summary. The direction register is the offset of 0. Right here, offset 0. And the output register is offset 4. So the base address is 0x440. So when you're writing to the output, the output that is going to be on the pins is 444. When you configure the register, when you configure the pin, you're setting the direction in setting the direction of the pin in this line of code here, which is offset 0 from 0x0440.
Why is it like it's just the way that the code itself is, to where it's not only shows like a 0x04, but here you have 0440. I guess the better example would be down to where we actually had to change that.
Okay.
And that's where it's 0x0444.
Yeah.
Where it's the 3 4s there, but on the other one it's just 2.04. Is that because why is it it's changing at the end?
Here in this code block snippet here, we are writing to the output register, which has an offset of 4. So you add that you offset that to the base address.
I get that part. I guess what I'm just trying to get at really quick is why is it here looking at 0444 with that 6 digits in the directory? It's only the 0x04.
No, this is only 4 digits. This is 4 digits after the 0x, and up here.
Not here in the AVR. I apologize. You go inside of the AVR, and that's the list. It has like 0x00, 0x01, 0. I'm just asking why is it shorter there?
Oh, in the instruction manual.
My apologies. Yes, it's short.
Oh, okay. Why is it short? The offset short here?
Yeah, that's all.
Oh, okay. Because they only need 2 digits to show the offset. You need 4 digits to show the base address, but only 2 digits to show the offset, because the offsets go up to 0x17. If you only needed 1 digit to represent the offsets, they would only print 1 digit. I see what you're saying now. Yeah, this is an offset, not, you have to add the base address to it. which is a longer number. So, all right, let's go ahead and see if this program will actually work. I kind of goofed on one thing. I put this in the wrong file. So I need to copy all this to Control C to main. V. Okay. And save all. Okay. So, got the board here. I went ahead and wired up a larger LED so it'd be easier to see. And it recognized the board. And go ahead and close that, and we can go to Tools, Device Programming. Tool, this one here, AVR 128DA48. Apply that. And then you're going to be programming the memories. Going to erase the chip. Why isn't it letting me cancel? Erase flash for programming. Erase now. Okay, I've erased it. It is not. Alright, memories. Why aren't you allowing me? What is the open file for programming? Oh. Forgot to do something. Forgot to build the solution. Kind of important, huh? All right, the programming center. Oops. Nope. Tools, device programming. Apply. Memories. Now I can program. And it's not working. It is not blinking. All right. So what could the problem be? All right. It's coming on. So the first interrupt is being triggered. It's not. Let's see. Let's see if we have the configuration right. Configure it and set the period to RTC. Set the compare. Enable the interrupts. Enable the timer. Let's look at the enable the timer part. Let's go to the RTC. Functional description, initialization. Oscillator control, desired operate, clock control. Configure the desired oscillator to operate as required. Write the clock select field in the clock select. Register accordingly. So the clock select has a 0, 0, which is the 32K oscillator. And then back to the initialization, go to the clock controller. And uh, the oscillator let's see here, what was the clock control peripheral, desired oscillator to operate as required. The default should work. It should be working there. Uh, uh, Control A register. We're not dividing anything. Run in standby mode is not an issue. Frequency correction is not an issue. Peripheral enable is what we did. Unless Any ideas why it would be turning on but not turning off? The clock is enabled. This was the enable the timer snippet of code right there. Yeah, the real-time clock oscillator is using the let's see here, the clock controller. We're using the OSC32K Control A register, and the only option for it is for it to run in standby, and this isn't running in standby, so that's not an issue.
So, I mean, somewhere in the code, right? You gotta have a line of code that has
080078, right? That register.
For this register?
Is that or was it binary?
Well, this one is at reset is at 0, so is 0 the default, the 0 is going to be the oscillator will only run when requested by peripheral or the main clock. And I requested the enabling the real-time counter requested that clock. I think, unless I'm missing something here. Operation initialization. Clock select field in the clock selection register, which is clock selection register, clock selection. Yeah, 00 is the frequency for the 32K oscillator. And that's the value on reset, so it should be selected. I'm wondering if there's a typo, just a simple typo. That it compiled fine, so we're running out of time. I will look at this and get back with you on Wednesday and explain to you what happened if I figure it out between now and then. But thank you for the input. Somebody is paying attention. Yeah, I guess we'll call it a day for right now. I will look at this and see where the problem lies. That I guess we'll just have a good day. See you on Wednesday.